Okay, so yes, so I'm Julie Wardlow and I study galaxies. So I do the part of the universe that Edward dismissed in one slide. So hopefully we'll talk about the rest of it now, but he's right, it is a small fraction, but it's an important fraction because it's the fraction in which we live. So what I'm going to do is tell you about galaxy evolution, but I'm going to show you where we get different data from. So every slide that I show an image of a galaxy, I've also got little thumbnails of where that data is from. And this video that's showing at the moment is just one source of some of the observations that we get. And this is the Very Large Telescope in Chile, which is actually 4 individually very large telescopes. And we can see the use of lasers here, which helps us to de-blur the atmosphere and get clearer pictures. But let's not talk too much about telescopes, let's talk about galaxies to start with. So when we're talking about local galaxies nearby to the Milky Way, and of course, astronomers' local is perhaps different to everyday world local, we can classify local galaxies or nearby galaxies fairly easily into these categories, mostly ellipticals and spirals, which you can see on the left and the right here. And so the ellipticals are generally red in color, they don't have much structure to their shape, and they're red because they contain mostly old stars. And then we have the spiral galaxies that, as the name suggests, they're spiral in shape, and they contain mostly blue stars. So they're very blue galaxies in comparison, and that's because their stars are young and they have ongoing star formation in them. And of course, our own Milky Way is one of these spiral galaxies. But the picture gets a bit more complicated as you look further and further away from us. So here's just a little cartoon showing that. So we've got our telescope on the left there. This happens to be a cartoon of the Hubble Space Telescope, but it could be any telescope. And as we look further away, we're actually looking back in time, because the light from a galaxy has taken usually many millions of years or billions of years to reach us, because light does not travel infinitely fast. And so it takes some time to get to us. And because these galaxies are so far away, that means that that time can be a cosmologically useful amount of time, or a cosmologically interesting amount of time. And if you looked far enough back, you could see just after the Big Bang. So what we tend to see is that galaxies close to the Big Bang look very different from the galaxies local to us, and that's because they've evolved over that time. And so one of the big questions in astronomy is understanding how these galaxies evolve and what drives the evolution, what causes, one galaxy to end up as an elliptical and a different galaxy to end up as a spiral, and those sorts of questions. So to give you a bit of a better idea of how this works in practice, I've got a video. And so what we're going to do is zoom in on one patch of sky. So this one patch of sky in that little box, and this is the ultra deep field. And everything I'm showing you here is real data, real images of real galaxies that are at their real positions. This is their true colors. And so you can see that local to us, because we're traveling away from the Earth in this video, so local to us, these galaxies have fairly classifiable shapes. So they tend to be spiral-like, or they tend to be elliptical-like. And you can see the variety of colors there. And as we get further and further away, so we're now getting more towards the edge of the universe, these galaxies on average are getting a bit smaller physically. Their sizes are reducing. And you can see that their colors are becoming much less diverse, and their shapes are becoming a little less easy to classify. There's a lot more in between galaxies. And so this is really telling us in a qualitative way about the evolution of the galaxy. So we've kind of gone backwards in this video from the Earth towards the Big Bang. But of course, what astronomers want to do is start from the Big Bang and say, well, how does this particular galaxy end up looking like it does near to the Earth? But astronomy is one of those sciences where we can't do experiments, because the whole universe is the experiment. We can't change parameters and rerun things in the universe. So instead, what we do is take snapshots of the galaxies at different times, so different stages of their evolution, by looking at different distances away from us. So that's different amounts back in time. And so then we can try and join all those dots really, and try and figure out the steps between galaxies at different time steps in the history of the universe. You can also, of course, run simulations. I'm not going to talk so much about simulations today, but they're an absolutely critical part of understanding this. And we use the simulations to sort of fill in these time gaps, and also to, we can use the data to test the simulations, and then in the simulations change some parameters and see what happens. So that's definitely a big part of it, but it's not what I'm going to touch on much. So this is all great, but what I've shown you so far is all what we would call optical data. So if you had giant telescope eyes instead of your normal, human eyes, this is the sort of thing that you would be able to see when you went out at night. You'd have to have very, very big telescope eyes, but you could do it. But that's not all there is to the universe, and that's not all there is to light. So here's a little experiment that you can do at home. So I've got my TV remote control here. I have to be careful which buttons I press because the TV is right next to me and I might accidentally turn it on. And you can do this yourselves, you can test this. So if you take your TV remote and you look down the end of it, there's a little emitter that sends the signal to your TV. So if you press a button and looked at that, you wouldn't be able to see anything. However, if you press the button and look at it with a camera, so if you look at my video feed right now, you should be able to see that flickering at the end. If I turn it off and then turn it back on again, you can see it flickering. And that's the signal that's coming out of this remote, and my webcam is able to detect it and send it to you. And that's because this remote control sends the signal to the TV by using infrared. It's just longwards in wavelength of what your eyes can see. So when you look at it and press the button, you don't see anything. With the exception of a few remote controls, they actually have a light on them, but most don't. So when you look at it and press the button, you can't see anything because your eyes can't detect that wavelength of light. But your webcam or your phone camera or other technology like that usually can detect it. And so if you look at it through that camera, you can see the signal being sent. So it's just one last go at it. Some new phones, and I say new, I mean within the last 3 or 4 years at this point, have an extra filter on, so they might not work. But if you've got different camera devices at home, you can try it with different things and see which ones you can see that infrared signal and which ones you can't. So that's just one example of where light at longer wavelengths would give you more information. So if we could see when I was pressing the button on here with our eyes without a camera, we'd see a different picture of what the remote control was doing than what we normally see. And the same is true in the universe. And in fact, if we look at the whole history of the universe and add up all the light that has been emitted in the history of the universe, and we look at that as a function of wavelength, we can see all of the emission from the stars and the galaxies and the black holes and everything else. If you add up everything in the optical range of light, which is what's shaded in blue here, you get a number. So that's how much over the whole history of the universe has been emitted at optical wavelengths. And then the red shaded region is how much light over the whole history of the universe has been emitted at infrared wavelengths. And you can see by eye here that they're about equal in size. If you add up the area of the red area and the blue region, they're about equal. And so that tells us that over the whole history of the universe, about half of all the starlight has been absorbed and re-emitted. So the optical light, everything was emitted originally in the optical. And then when it's been emitted, it's traveling through space and it hits a dust particle. And that dust particle scatters it. And then when it's scattered, it's re-emitted in the infrared. And so what we can then detect after it's had that interaction is only in the infrared. So that means that if we only study the universe using optical telescopes, we miss half of what is happening, because the rest of it's in the infrared. And so if we want to really understand what's going on, we need the infrared to do that. So that's kind of, maybe a little bit hypothetical. So let me show you a couple of examples. So there's 2 different galaxies here: Andromeda, which is our nearest big neighbor, and the Cigar galaxy. And Andromeda is a nearby spiral galaxy. And I'm showing you there 2 images, one in the optical and one in the infrared. And you can see that this galaxy looks entirely different in the 2. And if you only had the optical image, you might not realize, for example, in the optical, there's some dark regions in there, these sort of dust lanes down the sides. And if you add in the infrared data, you can see that these are the same regions that are really bright in the infrared. So if you only had the optical, you might think, oh, well, there's nothing in that bit of the galaxy. The infrared tells you, oh no, there actually is something there. It's been absorbed by dust and re-emitted in the infrared. So we need that picture to show us this extra side of the Andromeda galaxy. And similarly, the picture on the bottom is the cigar galaxy, and that's the same. So the optical here looks kind of pretty boring, you know, there's not an awful lot going on. As soon as we observe this galaxy in the infrared, you can see all this extra emission above and below the plane of the disk. And that's coming from the dust that's there and some outflows from that galaxy that are emitting very high energy particles that are then interacting with the dust, and we're starting to see the emission from that dust in those areas. But these two galaxies, you know, although they look vastly different in the two wavelengths, they're not even the most extreme sorts of galaxies that have infrared emission. There's in fact a class of galaxies locally called Ulurgs, or ultraluminous infrared galaxies, because astronomers are great at naming things. And they're the ones that don't tend to fit in very well in this classification scheme I showed you earlier. So there's just 8 of them shown here. And you can see that these are very, very messy. They're not clearly spirals, or they're not clearly elliptical galaxies. There may be mergers or interactions. They've got lots of bits being flung out all over the place. So locally, these sorts of galaxies, which are dominated by their infrared emission, and if you didn't look at them in the infrared, you wouldn't know that there was necessarily anything special going on. They're very rare locally. And so that was kind of the end of the story for a long time, that there's this rare class of galaxies that have a lot of dust emission nearby. And then in 1997, we got an instrument called Scuba, which went on the James Clerk Maxwell telescope, and that sort of changed everything. So Scuba was the first sensitive multi-pixel far infrared instrument. So sensitive meaning it could look at galaxies far away. Multi-pixel meaning that in 1997, it had a grand total of 37 pixels. Now, if you think about your average phone these days has tens of thousands of pixels. We had 37 with Scuba. But Scuba made a huge difference because it allowed us to look at the distant universe and see what dust there was in the distant universe. And if you want to, you can actually go visit Scuba, because Scuba has been decommissioned and it lives in Edinburgh now. So in the National Museum of Edinburgh, you can, or the National Museum of Scotland, you can go and see Scuba. And so you can see this instrument that really changed astronomy in many ways that I'm about to tell you. So these on the top are 2 of the first Scuba data sets, or Scuba images that came out. And between these this was absolutely shocking to astronomers at the time, because this showed that there's 9 galaxies that are really bright in the far infrared, or in the submillimetre, we call it, because it's submillimetre wavelengths, just less than millimetre. So I'm just putting arrows on those 9 sources so you can see them, because I think normally by eye they're hard to pick out, but those 9 sources was really shocking, because we expected about 1,000 times fewer than that. Because if you look at how many of these very bright infrared galaxies there are locally, you wouldn't expect even 1 in the area of sky that Scuba looked at. And you can even compare on the left with an image from the Hubble Space Telescope at the same sort of region of sky, just to show the difference between the Scuba image in the far infrared and the Hubble image in the optical. Of course, technology has improved since then. So now we're talking about images like this. So we've surveyed about 1,000 times more area since. This one's with Herschel. This is a tiny fraction of the total area that we have. And every single thing in here is a galaxy. So every bright spot that you see, that's a galaxy. And we call these submillimetre galaxies because they're detected at submillimetre wavelengths. And in fact, there's so many of these things, and they're so prolific and so bright that by the time you add up all their light, even the dark patches in this are filled with galaxies. So there's not really any true background here, because all the light from all of them kind of blends together. So let's look again at that comparison between the Hubble optical data and this far infrared data. So on the right is the original one I showed you. And on the left, I've just taken a tiny patch of that Herschel image that I just showed you, compared it to the optical. And you might be able to start to see one of the problems that we had for a long time here. And that is that it's very, very hard to go from a submillimetre image to an optical image and pick out, which one of these sources in the middle here is causing all that bright submillimeter emission. So what we had to do for many years was use statistical arguments and kind of try and figure out these correlations statistically. And that got us a long way. But in 2011, everything changed. And in 2011, we got an instrument called Alma, the Atacama Large Submillimetre Array. And this connects 66 individual dishes together. And these are in Chile in the desert. And so there's 66 individual dishes that they all work together. So you can see them in this video scanning the sky together. And that leads us to have an effective telescope dish with a 16-kilometer aperture. So instead of building a telescope that is 16 kilometers across, we can connect these 66 dishes and spread them 16 kilometers apart. And it gets us the same sort of data. So Alma allowed us to not just easily identify which optical sources are these submillimeter galaxies, but also to look in very great detail at what they look like at different wavelengths. So on the left here is data from the Hubble Space Telescope of some of these submillimeter galaxies. And on the right is Hubble Space Telescope data and Alma data. So on the right, we're looking in the red and the green at the existing stars, the old stars in these galaxies. And then the red is from Alma, and that's the new stars that are forming. So that's where the dust is. And so you can see that the new stars tend to be fairly compact, but they also, there's some morphologies there. So some of them are maybe, they have some elliptical or spiral type structure to them. But then looking at the optical data, they're a bit of a mess. So it's not really clear from this what these sorts of galaxies are. Alma also allows us to look at the gas, and the gas is what fuels the star formation. And so we can look here, these maps are showing the Alma emission and the gas, this is carbon monoxide, and how fast the gas is moving in different regions of the galaxies. And so the blue areas, they're moving away from towards us, and the red areas are moving away from us. And so you can see, for example, this one in the top left, that's probably showing some rotation in the gas within this galaxy. So that can tell us how fast the galaxy is rotating. It can also tell us how the gas is moving. But the thing that you'll notice from this and the previous set of images is that there's a lot of variety in the morphologies and in the gas motions between the different sources. So it's not really clear here what's going on, that whether there's some kind of standard picture for all submillimeter galaxies, or whether we can pick out different types of them, sort of subgroups, and figure out what's happening. So with all of the Alma data and everything else, we now know that these submillimeter galaxies, they're rare, but they were most common about 10 million years ago. So that's most of the way towards the Big Bang, given that the universe is 13.7 billion years old. But some of them exist really close to the Big Bang, so that we see some of these galaxies up to 800 million years after the Big Bang. They're extremely luminous in the infrared, but extremely faint in the optical, so that can make them difficult to study. And they contribute about 20% of the total infrared emission of the universe. So when we added up how much the universe has emitted over the history of its over its lifetime, about 20% of that is coming from this class of galaxies. This infrared emission is powered by star formation. So they form new stars about 1,000 times faster than the Milky Way. And they use up their gas supplies really, really quickly. So this suggests that they're going through a really intense but short burst of star formation. And they're very massive for their redshift. So for their distance, how soon they are after the Big Bang, they're really, really massive. So one hypothesis here is that they might be the progenitors of local elliptical galaxies. And you can see from the image in the bottom that local elliptical galaxies tend to cluster together or group together in what we call galaxy clusters. And so maybe these luminous submillimeter galaxies are the progenitors of local clusters. And that would be really exciting, because that would tell us one of the answers to these questions about why do some galaxies end up as ellipticals and some as spirals, and understanding how the evolution happens. So in terms of things I want you to remember from today, if you don't observe at infrared wavelengths, you miss half of what's going on in the universe. So we really need to do multi-wavelength studies to understand galaxies and to understand galaxy evolution, and to study, where we came from ultimately. there's this population of galaxies called submillimetre galaxies that are crucial for understanding galaxy evolution because they're massive, they're distant, and they have huge short-lived bursts of star formation. But they're still not fully understood. So we don't really know, are they actually the progenitors of these local elliptical galaxies? What triggers the star formation? Is there mergers going on or some kind of internal processes? And something that I haven't even talked about at all is about their black hole growth and what's fueling the gas and their environment. But in order to study any types of galaxy evolution and anything in the universe, we really need a wide variety of telescopes. So instrumentation is invaluable. And the thing I didn't talk about, which is simulations, is also really invaluable.